This is FE Peer Review. The date is June the 2nd, 2021. Ship on the Horizon, Part 1 of 2. This video is based on a nice observation I ran across. This video is based on a nice observation that I ran across by Robert Greenlee, who was at a hotel on a beach in Jamaica, and the hotel had many levels, at least 5 or 6. And there happened to be a big tanker type ship on the horizon. Robert had a Nikon P900 handy, so he took views of that ship from all the different levels, or from many different levels of the hotel. He did it as a continuous bit of film footage, video, but I'm just going to take snapshots from his video and look at them individually. I encourage you to go and look at his video. I let him know I'm doing this, and he was happy with it. He had no problem. So I encourage you to look at his video. There's a link in the description. Here we see what I believe is the 5th level above the beach. And then here we see the structure from the beach. And here he is standing near the water line, so I would put his eye level at about 2 meters off the ground. And I've indicated this as level 0. This is supposed to be pointing to the spot where he's standing, which of course we can't see. But I'm calling this level 0. And he's going to have an observation from this level 0, and then he's going to proceed to walk up these stairs and around the elevator and up to level 1, which we see up here, the balcony of level 1, balcony rail, where he'll do another observation. He'll then go across and go up to this level 2. You will see in his video, if you watch the video, this little arch object here. There will be an observation from level 2. So here's the observation from level 0. We see just the superstructure of the ship rising up above the water. That is level 0. And here we have level 1. We now see a portion of the main deck of the ship making itself visible. We will see, if you look closely, and we'll do a comparison later, you'll see that there is a certain amount of atmospheric refraction causing some vertical distortion in some of these elements. And here's level 2. We can see yet more of the hull of the ship and a bit of something coming up behind the superstructure. And now at level 3, which we didn't see in that earlier photo, but he continues going upward. He's now on level 3, and we have more of the lower portion of the ship visible. I'll take this moment to point out that all of this is happening over the course of just a few minutes, 3 or 4 minutes, and there are timestamps on these images. I don't have all the images in order. I reordered some of the later images. I'll take this moment to mention a couple of things. One is that there are timestamps on the images, so if you want to go back and look at his video, you can see that I've left the timestamp. Second, I want to point out that the ship is broadside to us, so his video only took 3 or 4 minutes. I think the total video was 8 minutes, but it's hardly 4 minutes to see all of the different levels. So in that 4-minute period, that ship would not have moved very much. And the fact that it's got its broadside to us tells us that it's relative to our position. Its distance is neither increasing or is increasing or decreasing very slowly relative to where we are, regardless of its forward speed, because we're seeing it from the side. So the changes we're seeing, I mention this because the changes we're seeing are not because of the ship moving, it's because we're moving. So this is level 3, continuing upward. He skipped level 4 and he went on up to level 5. And there's an image of level 5. A lot of nice detail here. So what I'm going to do with these images is I'm going to extract the bit of that ship where we can see the back portion with the superstructure, and we're going to look at trying to do some measurements. We're going to use some math. Everybody loves math, especially flat earthers love math. So we're going to use some math to see if we can learn a few things about how much farther we are seeing to the horizon line as we change elevation, and maybe even make a rough stab at some estimates on the ship's dimensions. I don't have fixed dimensions of the building that he's moving through, but I think we can use some reasonable assumptions to estimate, and then we can even test our estimate and see how much it would change if we were off by a meter or half a meter. So this video will continue with one slide, which I will go to next, and then in the second half of the video, in part 2, we will go into more detail on the analysis. Okay, so I've prepared this little slide, which contains two different solutions, a geometric and a trigonometric solution for the distance to the horizon. In this video, we're going to determine the distance to the horizon for our 5 observation points using the geometric equation, and then I'm going to touch on the trigonometric, which is a more exact equation, but in our case, with the lengths we're using, the approximate solution gives a perfectly adequate result. This is without refraction. We're not considering refraction here. This is purely a geometric problem. In the upper left corner here, I have a little diagram which represents our building and our observer. The green is the beach. Standing on the beach, our observer was at level 0, and his eye level was about 2 meters above the sand. Based on his movement through the building, I estimated that he went up about 4 meters to get to level 1. So that puts him at 6 above the beach. And then from there, an additional 3 meters for each level that he moved up the building, making his top position 18 meters. And I have indicated a line here which comes from his eye level, from his eyes, not his eye level looking straight out, but looking down towards the horizon, where the line of sight from his eyes is tangent to the surface of the earth. That is the geometric horizon. If you carry that line on, everything below that line is concealed. So this is the tangent. This is the distance we're interested in. From level 2, I've drawn another line, and its tangent is further to the right, so he's seeing farther. He's seeing that length versus that length. And from level 2, less of the ship is concealed. And finally, from level 5, he's seeing farther still. The horizon is out here to the right, and only a little bit of the bottom of the ship is concealed. This is the geometric solution. It gives the distance d from our observer point to the horizon. It's just simply Pythagoras' theorem. I've renamed the variables here. We're solving for d, and we are inputting various heights. V. R is simply the radius of the Earth. For the various heights I mentioned earlier, these are the solutions for the distance to the horizon in meters. I've done everything in meters, and these are the distances in kilometers. There's a slight approximation involved here because the straight line from observer to horizon is slightly longer than the arc length from H to V. But where V is very small compared to the radius, the two are so close that the difference disappears into the distant decimal points somewhere, so it doesn't really affect our solution at this scale. Here is the trigonometric solution, which is an exact solution. I won't go through it all, but here it is written out. And if you compare for V equals 2 meters, our observation from the beach, we get exactly the same answer using the trigonometric solution that we got from using the geometric. So those are two different ways to get the distance to the horizon. I skipped the shortcut formula. Some people like to use 1.23 times the square root times the height of the observer squared, whatever. I forgot how it goes. I skipped it just because it doesn't express the geometric relationships. It's convenient formula, but in practice, but it doesn't express the relationship. So I'm not using that one here. In the next video, the second part, we will look at how much of the ship gets concealed as he moves from one elevation to the next. And I think I will also touch on some atmospheric refraction issues that were in that image, how considering refraction would change our equations, and what it would mean for some kind of a perspective compression effect to be the cause of this. So come back for part 2. Thanks.